Good morning, everybody, and Tallinn, I think. I'm trying my best. Thanks for having me here. Thanks for being here. Let's go right into it. So I'm Martin. I work for a company called Archaeologic in Zurich, and I really love the web, and I'm really excited about what I'm going to talk about today. And you can see me here. Actually, that's not true. It's just me there. Anyway, so today we're going to quickly run through a few things. So first of all, why am I here talking about 3D on the web? Because that sounds pretty exotic, probably. And then we're going to see how that works, actually, from a technology perspective. And then we're going to give a quick get a quick intro on how that works. You might have seen, who here has actually used WebGL beforehand? Raise your hand, please. That's okay. So for most of you, it's new, and that's exactly why we have this WebGL 101 here. And then we're going to extend from just showing 3D content to actually immersing our users into a virtual reality in the browser, all from the comfort of your browser, including a little demo. If the demo gods are with me, I don't require internet because I have an app cache in there, so I should be safe. But browser dev tools, ooh, danger, danger, especially as it's beta. And now my clicker decided to stop. Okay, I can live with that. No, I can't because it's aha. All right. So why would you bother with 3D anyways? Well, you could ask the question, why do you bother with images and graphics, right? Why do you bother with painting things? Well, you can just use text. But that's not quite true, because if you look at it from a user's experience point of view, there is a reason why tweets with images or videos get retweeted more often or interacted with more often. There is a reason why articles with images and videos have a higher retention rate. That's the reason why Facebook and Twitter now autoplay videos, which is horrible if you're on a data plan in somewhere abroad. And the reason for that, the underlying fundamental reason for that is because us humans are social beings and we are really visual beings. So we rely on our first sense, which is seeing things. And it started off quite a while ago. I think that's IE 6 times, roughly. So people were discussing problems with getting the bull out of your code on IE 6. And then this was the browser wars. And this is service worker when it actually becomes stable. No, so basically, as humans, we have always been sharing stories and communicating moments. And the effort it took to communicate a moment has decreased dramatically. Back then, it took quite a while. I can't do that. I'm really, really bad at drawing things, especially when it comes to larger things on an uneven surface. So making this happen and communicating about this hunt that apparently has happened was a bit of an effort, right? You can't just do it with one click, really. This was better, so you could take photography, and obviously that evolved as well, because you had to stand still for a couple of hours, and then you only had to stand still for a couple of seconds, and you could capture a moment. The problem with both of these is these communications don't really show the actual moment, because the moment is a thing that happens over a certain period of time, so you only get one glimpse of that. But with videography, you could now actually take a moment in its entirety, so you could actually see how light it is to jump on the moon, which is kind of nice. And we took it further, and we're going to take it further in a bit as well. So virtual reality is on the brink of happening, and a lot of people might say, well, yeah, they said that in the 90s. Keep in mind, the New York Times has recently, for their subscribers, shipped Google Cardboards to their door. So each of these people, each of the subscribers of a certain plan of the New York Times in the US now has the capability to use their smartphone to emerge into a light version of virtual reality. So that's why we discussed this and why this is interesting. But so I mean, WebGL has been stable or considered stable since 2011, but yet we are not seeing that much content. And I, as a developer, a year ago have said or thought, well, you know, I see a couple of demos and I see a couple of cool games. There has been like a Quake port to the browser as well. But I'm not a game developer, and I actually have to build something that users want to use. So why would I bother with WebGL, right? I can do without it. Well, on the other hand, this is an article also from the New York Times about the Dawn Wall. And this is a brilliant piece on how 3D can enhance the story. So basically, if you're on a computer that doesn't support WebGL, you only get this in full screen, which is the article with photos and pictures and explanations. And I read through this, because I was using Canary, WebGL crashed, hello. And so I only got the article, and I was scrolling through it. I'm like, okay, yeah, that's nice and fine. And they talk about, oh, this is a horrible thing, and it has been so hard to climb up this hill, and it's an amazing effort to get up there. And then they have this one picture where they have a champagne party on this. And I'm like, yeah, sure, it's so hard to get up, but they still carry champagne bottles. How hard can it be? It looks like they sort of went hiking. It doesn't really. And then you see this interactive visualization, and it goes up the mountain as you scroll down. And you're like, oh, all right. No, oh, yes, that is a proper, okay, yes, okay, that's a proper mountain. I'm not going to go up there until they build an escalator or elevator. So here, WebGL was used to enhance the information and the idea of the article by providing spatial references. You now have a better understanding of space. Rather than from the pictures, you get a much better understanding of why this has been so tough to conquer. Another example is the tool that we're actually building. So this is a shameless plug. So we're building a tool that from the comfort of your browser, you can change furniture of apartments, and you give us a floor plan, and you get back a 3D model that you can visit and share from your browser, and you can modify it as you go along. And this is really cool, because from a floor plan, I have a bit of a problem to understand how the space actually looks. And with this, and if you then have a skybox as well, so you see how it actually looks when you look out of the windows, this is really cool and gives you a very different feeling. And we've run a study with users. So we did user testing, and 25% said that this could potentially replace an actual visit to a flat that you're interested, which is really cool. And again, this is about space. So a flat, an apartment, a room, a building, an office is a space. This is a space. And from images, I can kind of try to figure it out. But how often do you actually end up going into a space where you had seen photos and it looks very different from what you expect? For instance, if I take the picture from down here, it might look amazingly large. And if I take a picture with a slightly different setting, then it may look really narrow. But the space is the same. And that's because the spatial awareness that we're having is very different from 2D spaces. So this is really cool. But then, obviously, with all the cool stuff in the browsers, Service Worker and so on, and IndexedDB and WebSQL, we all have this problem of, can I actually use it? And the cool thing is with WebGL, it's actually not too bad. So iOS has it recently. We have it on the Android browser, Sims 4.0. We have it on Chrome Android as well. We have it on Opera. We have now actually on Opera for Android, but not Opera Mini as far as I'm aware. Safari has it. Internet Explorer has it since 11. Hey, at least something, right? Chrome and Firefox have it. It's really cool. WebGL 2.0 coming, giving us even more power. And Edge is interested in that as well. But how many users are actually being reached? Well, so there's actually an older version of WebGL, which is called the experimental WebGL. And take these statistics with a grain of salt, because this is actually from a website called WebGL Stats, which gathers data from websites that actually rely on WebGL being able to do their stuff. So it might be a bit skewed, but we're here at like 95-ish% as this is accumulative. So that's not too bad. So how do I actually use WebGL as a developer? Well, the very basic is to have a canvas. Who here has worked with the canvas before? Okay, if you have not worked with a canvas before, that's not a problem. The canvas is just a DOM element that basically is a piece of screen space. The difference between that and the div is the fact that you can address each pixel individually. So you can draw an image onto that, you can easily draw a line or a shape, a rectangular, whatever. You can draw on it programmatically, and you have pixel access that is accelerated. So that's quite nice. So basically, your JavaScript then writes through the CPU into the GPU that brings pixels onto screen. So that's pretty fast, and you can do games with it, or charts. You can do charts with that. You can use it to manipulate. So if you have seen one of those demos where you have your webcam picture and then you can apply different effects to it, that's either a CSS effect or a canvas. More often a canvas than a CSS effect recently. But it has a bit of a downside. Actually, the upside is you get pixel access. That's pretty cool. The downside is JavaScript is still executed on the CPU, and basically as it's single-threaded, you draw one pixel at a time, but you get direct access to the pixels on screen, which is cool. So it's fast, but it's not very fast. And the problem is, if you look at how the screen resolutions are today, so 720p has 921,600 pixels. And if you think about it, we want to run at 60 frames per second optimally. That means we have 16.6 milliseconds. The browser does some stuff as well, so it's sort of agreed on that we have approximately 10 milliseconds for our code to run to render an entire frame. Now, with 10 milliseconds and 921,000 pixels, that means that we have approximately 0.000011 milliseconds per pixel. JavaScript is fast-ish, but that fast? I don't know. So the cool shit is, that might be frustrating and shocking at first, but we are more or less the guy in the back. We're going like, we have a plan. And our plan is WebGL that uses GPUs. So what does that mean, it uses the GPU? Well, the GPU primarily is really frickin' fast to put stuff on screen, and that's actually what we want. So taking the GTX 980, which admittedly is a pretty recent and pretty powerful graphics card, but just to see how much excess power this thing has, it can fill 144 million pixels per millisecond. So that's this magical texture fill rate. It's not quite as simple as that, but it's the best number I could pull out of my head. So that's just filling texture pixels, so making things colorful, but actually there's a bit more work on top of that, so it's not that great, but still, it can fill tons of pixels in one go, and that does that because it has multiple cores that run in parallel. So basically, we are using functions that operate on each pixel in parallel. And this graphics card has 2048 cores that can run these programs that manipulate pixels. So they can run 2048 instructions at the same time, and they are clocked at a whopping 1.1 gigahertz. So that's pretty good. And this is how you actually leverage that. So this is the pipeline, and you see three colors. The blue boxes here are our JavaScript code. All the green boxes happen on this GPU, on the graphics card in your computer, or your graphics chip if it's a notebook or phone. And this is shader code, and shader code is red because it's not written in JavaScript, and it doesn't really, like, it happens on the GPU, it's going to be executed on the GPU, but we can influence this code, so we can write this code. But we're not going to write it in JavaScript, we're going to write it in what's called GL slang, GLSL, GL shader language, which looks a bit like C, but it's not too complicated, don't worry about it. It's actually quite friendly for its purpose. And what we do is, we have two arrays, basically, that we then ask, or that we then upload to the GPU using WebGL. One is an array of vertices, the other one is an array of faces. I'm going to explain what that is. But for the sake of simplicity, this is what we want to put on screen, a 3D object, for instance. And we upload this into what's called a GL buffer. So that's basically a piece of memory that is on the GPU. So it's really fast to access. So it doesn't have to go, the GPU doesn't have to go like into the RAM and back. No. It has a direct access to a piece of memory that is embedded into the graphics card. It then runs the first bunch of shaders, which is called a vertex shader. We're going to see what that is. For now, it's just a program that takes these informations that we passed in and mangles them in a way that we can use them later. We get out rasterized fragments, which is basically the parts of the screen that we're going to have to paint, that we have to fill with something. And then fragment shaders defining how this is being filled. So basically, the first step, the vertex shaders give us this triangle and this triangle and this triangle. And the fragment shaders then goes like red, green, blue, for instance. And then we have pixels on screen. And this happens in parallel and really fast. So quick vocabulary session, as there have been a few words that you might never have heard before. So let's start with coordinates. The coordinate system for a screen is rather simple, and you might have already encountered it in high school math. This is a plane, right? This is a plane field, and if I want to address this point, or if I want to communicate this point, I can say it's this far from the left and this far from the top, or this far from the left or this far from the right even, and this far from the bottom. So two things define this point on this particular plane. However, we want to do 3D graphics. So we're going to introduce a new axis. So now we're going to say, okay, I want to know, this point's cool and nice and fine, but what about this point? How do I communicate this point here in contrast to this point? Both are on the same distance from left and from bottom, but they're differently distant from you. Well, that's the z-axis. So basically I could say, this is, I don't know, 10 from, actually that's like 50 from the left, 50 from the bottom, and 0 away from this plane. And this one is 50 from the left, 50 from the bottom, and 50 from the plane. And minus 50 if I would go inside. And we have to sort of define points on this coordinate system, and that's what's called a vertex. Irregular plural, thanks English language, vertices. So one vertex, 4 vertices. So you see 4 vertices. They're a bit zoomed in, and it's digital zoom, so it doesn't look so good, but hey, so theoretically this is one particular coordinate on our screen in 3D, and this is 4 of them. Now I have these 4, and maybe I have even a couple more, but what shape do they actually make, right? I don't know, I can't tell. That's why we have faces. So here we have 2 faces. We have these 4 points, 4 vertices, and we have this face, which goes from this one, let's call it the first one, the second one, the third one, and the fourth one, so we can say the first face is from the first to the second to the fourth, and the second one is from the second to the third to the fourth. So we have 2 faces. So these faces allow us to specify the relation between the points, as in what shape is this actually, right? What shape do I talk about? And if we go back to the pipeline, that's our 2 JavaScript arrays. The vertices are the points. The faces are the shapes between them. Okay, that wasn't too bad. Now what the hell is a shader? Well, shader comes from the fact that you want to do shading. So for instance, if I have this surface here, if I have a box here, and there's a light shining from here, how is it shaded, right? How does the light affect the surface? But shaders have been generalized to do more than just that. And a shader is basically a function that runs on the GPU and runs for one thing at a time, and they can run it, each core runs one thing at a time of this shader, so this program is basically a function that is run on different inputs in parallel. So if our graphics card has 2048 shader cores, our function is going to be run 2048 times simultaneously. And there's two types of shaders. One is the vertex shader. So from the name you can kind of figure out, aha, so here I'm going to throw in my vertices, my points, and it's going to do something about it. Well, it's a function that takes a vertex and returns a different vertex. Okay, fine. So what it does is, for instance, you might want to figure out a camera. A camera is a concept that we're having, and if I say my camera is, I'm the camera and I'm facing this way, and you don't really want to draw something that is over here because it's outside of the camera. So a vertex shader can be used to do this for you. So basically you can write a function that figures out, is this vertex in the viewport of this camera or not? Oh, it's not. In that case, just transform it to a 0 thing, and then we just agree that the 0 thing will not be rendered. Or you could have a fish lens, which allows you to sort of warp everything. So you give in a bunch of vertices, and then this function then figures out, aha, I have to sort of, if it's 3 in a line, then I have to sort of make them look like this, and then it's going to return the modified vertices. And then there's a fragment shader. So in the pipeline, once we have all our vertices, we somehow need to color them in. These are the fragments. It has been called pixel shader, but it's not quite accurate because a fragment might not represent just a single pixel or something, but it might have, depending on how far away it is from the camera, it might be more pixels. So what this does is it gets a position along with a few other informations, and it gives back a color. So basically this function is called for each of the pixels that are going to be in this fragment. And then it calls this function, and the function returns what color this will be. So for instance, you could also pass along not just the position, but you could also say the angle that the light comes from. And then you can say, well, you know, this function will then basically use what's called the Lambert equation. So it's using the cosine between the angle of where the thing is facing, the surface is facing, and the light to figure out how much the light actually affected. It kind of makes sense. If I hold up a piece of paper like this, it's a tablecloth, but it doesn't matter. Like this, the light from the beamer affects it in full intensity, right? So the paper faces this way, my light goes this way, the angle being 180 degrees, big time influence. If I put it like this, it's not that much influence from the beamer, because it's facing this way, the beamer rays face this way, 90 degrees angles, cosine of 90 degrees, 0. So that's how you do shading. That's how you do lighting as well. So that's what shaders are. You can also use shaders to mine bitcoins. If you do that from a website, the GPU will be blocked and your Chrome will say WebGL has crashed. I tried. I mean, I didn't try it, of course. I just heard the rumor. So now, how do I actually get this? So we have the canvas, and for 2D operations, which is this, the CPU goes on each screen, on each pixel, I ask the canvas to give me a 2D context. If I replace that 2D context with a WebGL context, well, I get access to this nice and nifty pipeline of magic. The problem with WebGL is it's really wordy and it's a really complicated API because it's really, really low level and it's freaking boring. So what we're doing here is we create one of those buffers, which is basically the border between the blue boxes and the green boxes. This is where the buffers on the GPU will get created. We say it's an array buffer because we're going to put in an array of stuff. And we say, please use the triangle vertex position buffer, which is something that we created beforehand. Oh yeah, yes, okay, sure, sorry, my bad. Then we create a bunch of vertices. So this is 1 point, X, Y, Z, X, Y, Z, X, Y, Z. That's a triangle. That's a pretty boring one. And then we say, okay, the buffer data for this particular buffer, which is an array buffer. I don't know why you have to repeat it. We set it here. Ah, fuck that. So we have an array buffer, and it's going to be a float 32 array of the vertices, and it's going to be static draw, which means the content will not change, so don't worry about it. And then we say, okay, each item has 3 components, 1, 2, 3, and we have 3 of them, 1, 2, 3. Right. And we have nothing on screen with this code. I can't be bothered. If I would actually go to a point where we see something on screen, where we see the triangle on screen, talk to you tomorrow. But let's skip that. So there's libraries on top of that, Babylon.js, a ton of others, and 3.js. 3.js has been around for quite a while and is pretty widespread these days. And it takes away all this boring stuff. And basically it goes in the metaphor of making a movie, if you wish. So for making a movie, I need a few things. I need a camera. Got that covered. I need somewhere to actually shoot the movie, which is here. This shall be my scene. Got that covered. And we need something to actually sort of render the film that I'm going to put into my camera. And that's going to be my WebGL renderer. All right. And now I want to have something in the movie because just an empty scene is pretty boring. So for instance, I could take a chair, which is an object. In 3.js lingo, that's a mesh. Fine. And in the mesh, I define all the vertices, all the faces, and some material information, like what color does it have any textures, is it shiny, is it non-shiny, and so on and so forth. I put this chair onto my, or in this case, the box. I put my box onto the scene, and then I render using the I'm rendering the scene using the camera. And I do this on each frame. So if I did everything right, this renders with, hopefully, 60 frames per second. Now there's this useful thing that I built so that you can play it or try out things in the browser, but I'm gonna do it for you. That's the live coding part. So this takes even the entire setup stuff away, so you don't even have to download anything. You don't have to worry about NPM being slow on a hotel Wi-Fi or something. You just run it from your browser. And what I'm gonna do is I'm gonna do what I said or I showed in the previous slide. So I'm gonna do a new 3 mesh. And as I said, the mesh is basically 3 things: the faces, the vertices, and the material. because I'm lazy and 3JS developers are lazy as well, we put the meshes and the faces and vertices together as a geometry. And 3JS comes with a few geometries built in. So I'm going to use the 3-box geometry because I want a box. And this is just the size of it, and it's going to generate all the faces and vertices I need to have a box this size. And as I said, there's some material involved, so I'm going to go for a mesh basic material. Ignore the basic for a second. I'm going to explain it in a bit. And I'm leaving it out. Any defaults are sane, so this is a material that ignores light. The basic basically says, I ignore all the lighting. Screw lights are just going to be solid color. And if I don't specify any color, it's just going to be white. All right. As I said, I'm going to have to put this into the scene, and then I can render. And that's boring. But hey, let's make it less boring, because I could totally I could use a diff and CSS to make that happen, but I'm not. So to prove that, I'm using the rotation. I'm rotating, so we have these 3 axes: X, X, Y, and Z. And if I want to rotate the box like this, I'm rotating around the Y-axis. So that's what I'm going to do now. It's an absolute thing, so that means it doesn't mean like rotate around this by this much, but actually it says like the rotation is this much. And it's using radians, so 2 pi is a full circle, and we are running with 60 frames per second, so I want to make it a little less than pi, so this would mean on each frame it would spin by 180 degrees. So I'm making it a little slower. Actually, let's just use 120. And there we go. We have a rotating box. Still not very impressive. We can make a very 90s-ish box by making a wireframe that shows us all the triangles and vertices, and maybe adjust the color as well. Screen estate is precious on this one. So I'm using, say, green. There we go. So now you can see it has been 3JS split this up in triangles for us. On each side, it has all the vertices that are needed, nice and fine. Now, this is still a bit boring, isn't it? So how about making it a little more interesting? First of all, there's different geometries. So I could use, for instance, a torus knot geometry, which I think just takes 1 parameter to work. No, it doesn't. Geometry, yay! We take a torus knot geometry, and then we get this. I honestly have no idea who thought that this is a useful geometry, but it's the 3D equivalent of the pile of poo for UTF-8 talks, I think. Or we just, go back to a box geometry to begin with. Now I screwed up because I actually have to specify the 3 dimensions. So making this non-wireframey again, we can try something out. How about we make this more interesting? I talked about the Lambert formula, which is used for lighting. Let's use that. And guess what? Nothing. What has happened? Well, we don't have light. The mesh basic one didn't care because it ignores lighting, but if there is no light and you have a thing that relies on light, well, that's bad for you. So let's add some light. And I'm going to use a point light, which is basically the equivalent of a light bulb that just floats somewhere in space, and I'm going to make it green. I'm going to say this shall be, just use it. I'm going to position it around a bit, so I'm going to, where do I put this? I'm going to put it above the, actually I can use set, so that I can use all 3 dimensions. So I'm going to have it minus 100, 100. So I'm putting it to the left, above, actually make this 150 just for shits and giggles, above and a little in front of it, I think. And then I can add the light to the scene as well. And there we go. And now you can see that the light has an effect on this box. Maybe if I put it in the center again. Yeah. So now we see that the light influences how the color comes out, right? So this box is actually white, but there's only green light. So what happens if I do this again and get me a second light? I'm going to imaginatively call it light 2. And put this one into this scene as well, but I use a different color. What if I use red? Then we can see that the lights, oh actually now the lights collide a lot, so they basically overlap too much, which is not a problem because I can specify how far they shall shine. So I'm limiting them a bit. Oops, wrong one. Nice idea, but no. The cool thing is JavaScript would have gone like, yeah, extra parameters, look at me, I don't care. Okay, that's not far enough. See, I can never remember these parameters. Oopsa. Okay, this is bad. I forgot the parameters, but that's not a problem because, oh no, that's actually the wrong one because I'm super prepared. So here, what I'm doing is I cheat to begin with. So what I'm doing here is I have my box again, I have a basic material, I have another box that uses a Lambert material, and I have a third box that uses a Phong material. Phong is a different equation that actually allows you to have a shiny material. Lambert is non-shiny, it looks a bit dull, and if you have a metal material, then you want to use the Phong shading, which is built into 3JS. It's very shiny, as is WebGL, and it shall be a metal. And then I put these three next to each other, and I have a few lights positioned accordingly. We have a red one, we have a green one, and we have a white one. And all meshes rotate, and here you see the difference. And it's quite extreme, isn't it? So all of these three are white. This one ignores lighting in total. This one uses Lambert, it's non-shiny, and this one is a metal box that is pretty shiny. Probably a bit too shiny. So that's what shaders are for, really. But do I have to limit myself? Do I have to limit myself to these boring, simple shapes? No, of course I don't. So there's a few loaders for different 3D file formats. One of them is the OBJ loader, and OBJ is basically two files. You have the OBJ file that defines the vertices and faces, and then you have the other file, that's the MTL, that defines how these are sort of colored and shaded. So I'm going to get myself a loader, which is accordingly named 3JS OBJ MTL loader, and I ask it to load something for me, and now I give it the OBJ, and I give it the path. I hope now actually I do rely on internet, so and I get a callback with the object. And actually this is a bad idea. I should do it with the whatever. I know what I'm going to do, because the materials will try to or will use light. But I can't be bothered to figure out what light I actually want right now, so I can do a new 3 ambient light, which is just the light that colors everything. And if it's ready loading, I know that this one is a bit too large, so I'm making it a little smaller. I'm actually making it 25% the size that it is. Then I add it to the scene, and obviously it doesn't work. Now the question is it because it's loading this OBJ file in the background, or, oh, there was an error. No, it says OBJ MTL loader is not a function. OBJ MTL loader, I'm pretty, oh, maybe because so this editor does a few tricks. So maybe mesh is not defined. Oh yeah, that's true, but at least my spaceship has appeared. Let me quickly get rid of my DevTools again. Oh, the button is over here, isn't it? No, what the hell? The window is apparently larger than the actual screen. Closing that. You know what? I'm gonna. No, it stays. Go away. Screw this. I'm gonna reload. I'm not having any of your shit. Not yours, but the shit of my browser. So, fine. Whatever you wish, browser. Whatever you wish. Bleh. Pfizer, ship. OBJ. Why didn't I just call it fish? Would have been so much easier now. Function. Thing, because I just can't be bothered. And then obviously I'm not rotating it here because I can't. Scene, add, thing. I'm not even resizing it. Let's see what, oh yeah, I don't have light. Nah. New 3, ambient light. Now I do. Yeah, sure you do. Maybe because it's actually still too large. Thing. Thing, scale, set, 0.25. You actually scale it along the 3 axes. And it just goes, nah. So what did I do wrong this time? Oh, Jesus. Yes, I'm repeating a mistake made previously. New is just annoying when you forget it. Yeah, okay, so it's a bit larger. It doesn't do much yet, so let's say we actually use hoisting for the win. And now I can say if it has loaded, then y plus equals math pi divided by 100. So I have a weird read. What the hell is this? Oh, I scaled it to 0. See, you can totally do it and it totally makes sense. It just looks hilarious when you do it. It crashed into something. So you get this beautiful rotating thing. You can use your keyboard or mouse to add controls, and voila, you might have a game at some point. There's a few more examples on this one. I highly recommend checking it out. So to not run out of my time frame, virtual reality. This looks hilarious, but it's actually quite cool. It's the bird simulator. You can buy it. Has been on my wish list since I was a child. Not. Anyway, so this is a more or less creepy version of that. She's on she thinks she's on a helicopter, facing down onto the street, and it's mobile, and it's using the Samsung Gear VR, $99 I think it is, if you have a Samsung device. And the difference here is, so 3D is nice and fine, but you're always in front of it, so you're in your environment. And when I was a child and I was playing a computer game, a really badly graphic computer game, but still, I was driving a car and I wanted to check if someone's next to me, so I actually looked out of the window and went like, huh? This problem is solved by virtual reality. You can actually look around, which is convenient. It has decreeped itself. So 1962, something that you totally would put in everyone's living room, right? So someone said, no, we need a headset. So this is the headset from 1968. It's attached to a large apparatus that actually holds it onto a bunch of cables. It looks absolutely creepy. It looks like they removed his eyes or something. Wouldn't wear it. It's like, hey, wear this. Like, hell no. And then slowly back out of the room. Always facing them so they don't attack me. 90s, mid-90s came, Sega tried it, and 97, Nintendo tried it. Nintendo Virtual Boy pretty much flopped, and they said it's because of the price. If you would adjust the price to today's levels, you would get $273. This one costs $350, go figure. But this one costs $5 with your phone. It's really cool. And you can do things like this with this. This is an apartment that hasn't been built. Awesome. This is a cathedral in Barcelona, not Barcelona, in Palma de Mallorca, and this is my fiancée. And she doesn't even know that she's in the picture, I think. I should probably tell her at some point. And it's really, really cool, and you can give that to people. And this is how you do it when you use Three.js. You have a VR effect on your renderer that you already have. You have VR controls which do the panning. If your phone rotates, for instance, you update them on each frame, you render them. And here's Chrome working for Oculus, Chrome and Firefox nightly builds. Chrome has special builds from a Google Drive folder. There's a brilliant mailing list with help. Here's a few resources on that. The second and third one you can try out your own. There's a few open questions. Biggest question being a lot of people have to vomit when they use VR right now. We have to fix that. This little fake nose here actually reduces the amount of people that vomit. That's pretty cool. We don't know much about designing for it yet, but there's guidelines from Google to make an effective UI. To wrap up quickly, WebGL has solid support, which is really nice. It makes sense when you have space and you want to talk about space to represent it as space as such. WebVR is a big thing. It's very unstable right now, but definitely give it a try and play around with it. If you have a phone, get yourself a cardboard. It costs really $5. Get yourself a cardboard. And it's a playground with lots of challenges. It's the final frontier right now. We don't know what's going to happen next. So that's it from my side. Thank you. Sorry, no. One last thing. One more thing, as he went. Steve Jobs said the computer is the most remarkable tool that we ever come up with. It's the equivalent of the bicycle of our mind, for our minds. I want to adapt that and say VR is the second most remarkable tool that we've ever come up with. It's the teleporter for our minds. Give your users superpowers with all sorts of technologies. This one is a particularly promising one. Thank you very much. I'm sorry that I had to rush a bit. Slides are already online.